Okay, let's talk about range. So last class, we were talking about domain. And really, when I think of domain, I just think of what are all the x's allowed to be? Or I guess more generally, the inputs. What are you allowed to put into a function? And kind of contrasting that, the range is everything you get out. All the outputs or all the y values is kind of the easiest way of saying it. So when I look at the range, I'm thinking, okay, essentially, what y values I'm getting? Well, I'm going all the way down to negative infinity and as high as positive 34 for this first example that I already wrote the range for. And I do actually get positive 34 in my range because that function hits the value of 34. If I look over here, I will admit, I tried to make this first one maybe a little tricky, not that tricky, but I tried to use some extra points so you don't really need to find the range. But I'm thinking about the range, I'm just thinking about how high it goes, which is clearly off to infinity, or I think it's clear. And then we can just kind of see how low we go. Well, it looks like we go as low as -2. And we do actually get that -2 value. So here the range would be everything from -2 inclusive all the way up to infinity. On the other hand, for this function here, if I start looking at the range again, well, we're certainly going down to negative, like this, the arrows like this indicate we keep going in that direction. So we're definitely going down all the way to negative infinity, and we're going as high as almost 3. We're not quite ever getting to 3. So what we would say here is that our range is going to be everything from negative infinity up to 3 exclusive, because we don't quite ever get to 3. We get really close to 3, we never actually get there. So when you're thinking about range graphically, you're really just thinking about what y values am I getting. Really, I would say just like domain, you're really more thinking about what y values am I not getting, kind of like when I think about domain, I'm definitely thinking about what x values do I not get to have, and then I go on and think about what x values I do get to have. So in that context, let's look at some more examples, because definitely, at least on this first homework assignment, there's quite a few questions about domain and range. I think it's worth observing or worth looking at. Yeah. We'll try and kind of hit some of the highlights. So I looked at her class notes yesterday, and it looks like there's a lot of stuff about like graphing and how functions work and that kind of thing. We'll try and hit some of the same highlights. I will tell you, most of the time, this first like week or 2 weeks of pre-calculus review is done under the assumption that you all already know all this stuff, which may or may not actually be true. I'm going to try and give a little bit more nuanced and detailed descriptions of things. That said, so sorry, I'm just noticing that there's this weird like white bar on the side here. Oh, I see what that is. Okay, it's like, what is that? It's my window here bleeding over. Sorry about that. Okay. If there are things you would like me to talk more about, like trigonometry or something like that, let me know and I can talk more about it. But I have plans. I got things to say, so we will do that, and then. But I can certainly do more or less of anything you would like. Let's talk about some functions and their domain and range. So usually we talk about domain and range kind of together. Let's look at something like f of x equal to. This does feel a little low. Don't want to punch it over. The square root of 144 minus x squared. And I want to find both the domain and, after graphing it, the range. There are other ways of finding range, but for now, we're going to limit ourselves to just finding range graphically. And to those of you that just joined us, do fill out the attendance form when you have a moment. So, domain first. I see a square root, and I know when there's a square root, we have to say that the insides are non-negative. So the insides, 144 minus x squared, needs to be greater than or equal to 0. And there's a couple ways you could do this. I personally recommend factoring. I don't like taking the square root of both sides when it's an inequality. It's a little bit dicey. So I'm just going to factor this, and I notice that 144 is 12 squared, and x squared is x squared. So I have a difference of squares. This is really 12 minus x times 12 plus x. The order does matter here. I definitely have seen many students in the past factor this as x minus 12 times x plus 12, which isn't quite the same thing. right? If I FOIL this back out, I get 12 times 12, which is 144. I get minus 12x plus 12x, which cancels out. And I get a minus x times a positive x, which is minus x squared. So the order definitely does matter. And then I guess we would do the number line thing we were doing last time. So what's going to go on my number line? Somebody help me. What's going on the number line? And exactly, right? Just the zeros, the things, yeah. And then we test points. And so remember last time we were saying how you could test points all the way, or you could look at the powers of the factors. What are the powers of each of these factors? Right. They're all one, so it means they're all odd, which means the sign's always going to switch, change, yeah. So if I pick something over here, like, I don't know, 20, 12 minus 20 is negative, 12 plus 20 is positive, and a negative times a positive is negative. And then we know it's going to change signs and change signs again. If you think about this for a second, you might also think about the fact that if you just looked at 144 minus x squared without the square root on it, that's a downward opening parabola. And the downward opening parabola definitely goes negative, or I guess from left, right, starts negative, maybe goes positive when it crosses the x-axis, and then goes back to being negative. So it makes sense that it's negative, positive, negative. You're kind of seeing a graph that might look like that. If you were graphing, can you see that? I feel like it's not very good. There would be a graph kind of like that. So we only want the positive parts though, right? Negative is not okay if it's inside a square root. So we just want the positive parts and the zero parts. So our domain here is going to be everything between negative 12 and positive 12 inclusive. Now we're going to try and graph it. And this one, you could, yeah, I gotta say a couple things here. So I'm going to plot a few points. There's some easy things to plug in. I can definitely plug in negative 12 and 12. When I plug in 12, I get 0, right? F of 12 is certainly the square root of 144 minus 144, which is 0. And so is f of negative 12. It's also 0. What's another easy number to plug into this function? Or really any number I could plug in. I have a specific number I'm thinking of. But we could plug in other things, right? We could plug in 2. It's not great. F of 2 is the square root of 144 minus 2 squared. Okay, that's the square root of 140. I mean, that's a number. I don't know what it is. It's less than 12. It's bigger than 11. But what's an easy number that's going to give me a nice result? I know you know it. I know you just don't want to say it. If I was going to, let me ask you different. I'll ask it this way. These are my x-intercepts, right? If I plug in 12, I get 0. If I plug in negative 12, I get 0. How would I find my y-intercept? Write it on your paper. Think about how to find the y-intercept. So if I'm graphing this thing, I'm going to start graphing it. So I've got 12 comma 0 over here, where x is 12 and y is 0. And negative 12 comma 0 over here. And there's going to be some y-intercept. I'm going to find it by, well, if I'm on the x, sorry, if I'm on the y-axis, x has to be 0. It's usually a go-to point we try to plug in when we're graphing something, because it's usually it's kind of required. People are like, if you're going to graph a thing, show me where the intercepts are, just because they're usual information. And if we plug in 0, we actually get a nice value out, because f of 0 is going to be square root of 144 minus 0 squared, which is just the square root of 144, which is 12. So we've got the point 0, 12 up there. Now, normally I wouldn't care too much about graphing this very precisely, except that this is a specific shape that you all should be aware of. So this graph is actually going to be the top half of a circle. And the way you can see that is by doing the following. If you look at, I'm going to use y instead of f of x. You look at y equal to the square root of 144 minus x squared. If we square both sides, we get y squared equal to 144 minus x squared. And if we add x squared to both sides, we get x squared plus y squared equal to 144. And that's exactly the equation of a circle centered at the origin with a radius of the square root of 144. So this is a circle centered at 0, 0 with a radius of 12. So this function here is the top half of that circle, because when you do y equal to the square root, y has to be positive. So we only get the top half instead of the top and the bottom half. So this looks like, I draw it all right. Pretty good. Maybe. Spoke too soon. The top half of the circle. And we can certainly look at this and see what the range is. The range, well, how low do my y values go? That much. 0, as low as 0. And how high do we go? Why can't it go down? That's an excellent question. Give me 1 second. So the reason we can't go below the x-axis here, actually, let me ask you to clarify. Do you mean why are we not getting the bottom half of the circle, or why is it not going like further this way?
Yeah,
right. So there's kind of two good reasons for this. One reason is that, and we talked about this a lot on Tuesday, not that I expect, like, just as a reminder, when you take a square root of something, you always get what kind of results? Like, what's the square root of 9? 3. Never negative 3. So when you're taking a square root of some stuff, you can only ever get positive y values out. So that's one reason why we can't keep going further down this way. The other reason we can't keep going further to the right is because our domain ends at 12, right? We are stuck between right, here's our domain where x is between -12 and +12. So two good reasons why we don't go that way. I will say, just to kind of extend that question a little bit, if we were just graphing 144 minus x squared, then you would get the whole parabola shape that does go down in that way. But I was kind of illustrating that to show what our domain looked like. So here our range is going as low as 0 and as high as the highest y value, which is 12. There's our domain and range for this function. Cool. I was going to do that. Let me pin my video. All right, let's look at some more examples. Let's look at something that's a little bit more, yeah. Well, that one's kind of funky. Sure, that's fine though. Yeah. Trying to move this back a little bit. I try to keep what I've done on screen, kind of, and new stuff. Sure. Okay, so let's look at another example. Let's say we want to find the domain and range. What have I got here? Wrote something down. Yeah. G of x equal to x squared minus 8x plus 13. All right, so this is a quadratic function. There's a lot of names. Oh, there's a question here. Sorry. Whoops. 1 sec. Sorry. If I don't see something in the chat, definitely let me know. Quick question unrelated to the content. I signed up to the co-class, not realizing it directly conflicts with my biology. However, I still, yeah. You're welcome to come as you will. If you can't attend live, that's totally fine. You're welcome to watch the video later, fill out the attendance form, whatever. But yes, you do not have to be here right now. Right now, I mean, obviously, it seems like right now works for all of you right now. But maybe in 3 weeks you have a midterm right after class, and you don't want to be here before your midterm. That's totally fine. You don't have to be here. You can totally watch stuff later. So yes, you can totally do whatever you want. Come when you need to. Come see me. Yes, you're welcome to get all the help when you can. So g of x equal to x squared minus 8x plus 13 is a quadratic. It's a polynomial, right? Polynomials got all positive, actually let's say non-negative integer powers of x. That's what makes a polynomial, because all the variables are raised to non-negative integer powers. When that's the case, well, in fact, I didn't even say that really. When we talk about domain, do we see any of the usual domain problems? Do I see a square root? No. What else do I need to worry about? Logarithms, definitely no logarithms. What's the other thing I have to worry about? Right, specifically dividing by 0, and there's no division by 0 here possible. So we're safe. There's no domain issues. that means our domain is going to be everything. You can either write that the usual way in interval notation is writing it like this, with everything from negative infinity to positive infinity. But some people like to write it faster as this fancy R with 2 vertical lines instead of 1. This just is a symbol for all real numbers. All right, but then we have to talk about range. So we have to graph this thing. And I didn't pick a very nice one, kind of on purpose, not really though. So how good does our graph have to be? Well, if we're just trying to find the range, not that good. I'm not going to worry or too much about finding all the x-intercepts because I think they're kind of gross. Because I think you might notice that this doesn't factor, right? There's no way to multiply the 13 and add up to -8, at least not with nice integer numbers. So I'm going to think about graphing this. So to graph any quadratic, there are 2 things I'm always going to think about. Thing one, the most important piece of any parabola or any quadratic, in my opinion, and I'm right. So usually I'm like, different opinions are fine. If you do it a different way, totally fine. But I'm very convinced about this one thing, that the most important point on a parabola is definitely the vertex. And I if you disagree with me, we can talk about it, and I will tell you how wrong you are, and you can go on. But the parabola, definitely the vertex is the most important point. So to find the vertex, there's a couple of ways to do this, but kind of the easy formulaic way is to say, well, the vertex has an x coordinate, which I like to call v sub x, and a y coordinate, v sub y. And specifically to find the x coordinate, you just take negative b over 2a, where of course, I didn't say the things, but I think you all know what I mean. B is the coefficient of x and a is the coefficient of x squared, right? So this is our ax squared plus bx plus c. So in this case, our b is -8 and our a is +1. So -8 over 2 simplifies to 4. Yeah, question.
I can't see the vertex like above the v.
Oh, that says parentheses v sub x and v sub y. Sorry. Right. I need to write, I need to write bigger, I think, is what I really need to do. That's a v with an x as a subscript, and that's a v with a y as a subscript. So there's our v sub x, it's just 4. And then to find the y coordinate, we're just going to plug that 4 back into the parabola or the quadratic function. So our v sub y is just going to be what you get when you plug in 4. So g of 4 is going to be 4 squared minus 8 times 4 plus 13, which is going to be, let's see, 16 minus 32 plus 13, which is -3. So great, that's the vertex. Let me ask a couple questions. Which way does our parabola open? Does it open upwards or does it open downwards? Upwards. And how do we know? Because, yeah, the leading coefficient is positive. So if it's if it was a negative x squared or a negative 3x squared, it would open downwards. We know this opens upwards. So that vertex is going to be the bottom of the parabola. So whatever our parabola looks like, we know at the point 4, -3, that's the bottom. There's our vertex. And the only other point I'm really going to worry about, if I'm just trying to do a not great job of graphing it, is the y-intercept. So the y-intercept we get by setting x equal to 0. And if I set x equal to 0, y is going to equal 0 minus 0 plus 13, which is just 13. Usually the y-intercept is pretty easy to find in most functions when you just set x equal to 0. So it's somewhere up here. Again, I'm not really caring that much about doing a good job. I'm just trying to kind of graph it. Now I will say, usually when I graph a parabola, I find the x-intercepts. We could totally find them. They have to exist, right? Because the vertex is below the x-axis and it opens upwards. To find the x-intercepts, you would set the whole thing equal to 0. In fact, actually, I know I wasn't going to do it, but let's do it anyway. So to find the x-intercepts, we are going to set y equal to 0. And if we do that, we're going to get x squared minus 8x plus 13 equal to 0. And if we could factor it, we would. We can't. So when you're trying to solve a quadratic equation and you can't factor it, what do we have to resort to? Everyone's favorite formula, the quadratic formula. Yeah, yes, exactly. I know. It's not that bad though. So here our solution would be x equal to -8 plus or minus the square root of -8 squared minus 4 times 1 times 13 all over 2 times 1. In case you don't remember the quadratic formula, this is a reminder, the general solution is x equal to -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. That is your quadratic formula. And I don't really care what this is, but I do want to point out that it is a real number. If we simplify this just a little bit, we get 8 plus or minus the square root of 8 squared is 64. 4 times 13 is not a number I feel like most people would normally know, except if you've ever played with a deck of cards, you know that there are 4 suits and there's 13 ranks in each suit. By the way, that information will come back up at the end of 17C. When you talk about probability in 17C, I know it's kind of weirdly tacked on at the end, but in 17C, we will talk about probability, and card games are just a natural source of good problems for probability questions. So if you haven't played with cards before, I encourage you all to at some point this quarter, next quarter, before 17C, whichever way you take it, play cards with some friends, play cribbage, play something, just so you familiarize yourself with a deck of cards. You know, there's 4 suits, aces, clubs, diamonds, and hearts, and there's 13 ranks, ace through 10, jack, queen, king. And 4 times 13 is 52, which is the number of cards in the deck. It's also twice the number of letters in the alphabet. I know it seems like a dumb thing to say, but it's useful. So I've got 64 minus 52 all over 2, and that simplifies to 8 plus or minus the square root of 12 over 2. And again, I don't actually care what number that is. I just care that it happens to be real. I'm taking the square root of a positive number, so things are good to go. So those would be those points there. Okay, but I kind of got away from the question, which was to find the domain and the range. So now that we've graphed it, and this is why the vertex is really the most important point. Now that we know that the vertex has a y-coordinate of -3, we can see that the range goes as low as -3 and has no upper limit. It just keeps going and going. Oh yeah, let's look at that one. Okay, more examples. Let's say we have, I feel like I made this one extra tricky. Let's make it a little less tricky. Let's say we have the following function. H of, let's number things. H of t equal to, no, I like it that way, fine. We'll do the tricky way. 24 minus 5t minus t squared over 3 minus t. Question. Oh, sorry. It was, so the range was, if we look at our graph here, right? How low are we going? How high are we going? It looks like we're going as low as -3, all the way. Oh, something I should say, just because I haven't said it yet. Whenever you're writing interval notation, it's always the lower numbers on the left and the higher numbers on the right. Kind of like how the number line is set up, right? We put the lower numbers on the left, or the more negative numbers on the left, or the less positive numbers, and the higher numbers on the right. So one second. It would definitely be, I wouldn't say wrong, but just not right to write this as infinity to -3. It's wrong enough that it's not right. So we don't want to do that. Yeah. Oh, sorry, Lily first. Well, because so when I talk about that's a really good question. So the domain here definitely is everything, right? The x values go from, x is, like way out here. Like if x was -1,000, the y value would be some large y value. But as we get closer and closer here, like when x is 0, the y value is what, 13. When x is 1, you get something. When x is 2, but the x values are everything. The y values, however, though, this is the lower limit for y. Right? This function doesn't go any lower than what's the lowest value I get here? -3. So that's why -3 is the boundary of our range, because the range is the what values, the x or the y's, the y values. And so if we think about this being the y-axis and this being the x-axis, the y value is, oh, the lowest y value I get is -3. I can't go any lower than that. Kyra.
So,
Megan?
I just remember like in high school, they would say, oh, range is just like bottom to top and then.
Right, I would say that as well. So definitely here, right, the range of this function is the bottom, which is -3, to the top, which is, there is no top in this one. It is a common mistake I've seen would be to say that the range was like 4 to infinity, because you get the wrong point. So when we're talking about the range, you need to look at the second coordinate, which is the y coordinate. Talking about domain, we're looking at the first coordinate, which is the x coordinate.
So if the parabola was going down,
Sure.
it wouldn't be negative infinity to.
No, you're correct. It would be. So just, yeah, just to kind of, in fact, I think that was, if you look back at the, I mean, you might have missed the warm-up actually. If you look back at the warm-up problem that I started with this parabola, which I didn't write the function for, but this parabola certainly had a vertex at 4,34. And the range here was -infinity up to a y value of +34. So yeah, so if your parabola opens downwards, it's going to be -infinity to something. If it opens upwards, it's going to be something to infinity. And just like I was saying, always the smaller numbers on the left, or the more negative numbers on the left, the bigger numbers on the right, or the less negative numbers on the right. Yeah.
Will it change if there's a hole?
Yes, holes definitely, holes, yeah, but you asked the perfect leading question for this next example. Why, thank you. What a good setup. So if we look at this function here, if we're talking about domain, I believe all of you, in fact, everyone can show me on their fingers, what t value should I exclude from the domain? Show me on your fingers. Yes, that many fingers. Yep, that many fingers. Cool. Yes, that many. Right. You write it in the chat too if you want to. But yeah, we definitely don't want 3. Now, really, the work I would have done if I was being a little more explicit was I would have said, okay, domain, the denominator can't equal 0, or I like to exclude where the denominator is equal to 0, which would have then led me to excluding t equal to 3. So we're getting t not equal to 3. And then if we're going to write it in interval notation, we're going to say, well, it's everything but 3. So I like to write the number line. I don't know. I just do. I will point out, when you're writing the number line, you don't need to include 0 unless it's actually an important point on your number line. I'm not going to write 0 unless it happens to be something that's like one of the things I need to worry about. So here, 3 is the only issue, and then I literally want everything else. So my domain is going to be all of this and all of that. So everything from -infinity right up to 3, except not 3. And then everything from starting at 3, except not 3, all the way to infinity. It's kind of tedious to write all that out, but you should. I definitely can't recommend writing it like this. I mean, I hesitate to even say it, but I'm going to say it anyway. R minus the set containing 3. Some people like to write that when they're feeling kind of lazy. It just says all real numbers except for 3 or -3. But I don't recommend that. It's not interval notation. So if the problem says use interval notation, we are forced to it. And I think that's definitely what WebWork is looking for, is interval notation. Okay, but now range. This one doesn't graphing this thing seems challenging. It's a rational function, which requires a little bit more, I think, work, but there's a trick here. The trick is that we should factor this thing to see what's really happening. So factoring, I knew I picked something I didn't want to do. So if I've got 24 minus 5t minus t squared over 3 minus t, I don't love the way I've written the top part here. I don't like factoring things when I have a negative t squared. I know it can be done. I know I've done it, but it's harder, and it's harder than it actually needs to be. So what I could do to make my life easier, which I'm going to do, is I'm going to factor out a -1. I'm going to write this as -1 times t squared plus 5t minus 24. And I might as well do the same thing on the bottom. That's not a very good reason, though. The reason I'm really doing this is I know what's going to happen like this. I'm going to write this as -1 times t minus 3. And hopefully you all agree with me that I have the same thing as I had before. Right? It looks a little different, but it's still the same. And now it's much easier for me to see how this t squared plus 5t minus 24 factors. In fact, I could even cancel the -1 if I really wanted to. I do want to. So I'm looking for numbers that multiply to -24 and add up to +5. And 24 is a tough one. 6 and 4. Oh, yeah, what? 8 and -3 are the winners. Exactly. Multiply -24, add up to +5. So we've got, this is going to factor as t plus 8 times t minus 3 over t minus 3. And oh, look, the t minus 3's cancel. So here's what I want to say. This is kind of an important distinction here. My function h of t is equal to t plus 8 with the exception that t is not allowed to equal 3, which we already knew because we knew that t equal to 3 was not in the domain. This is an important thing to know. When you simplify a function, cancel some stuff, whatever, that doesn't change the domain. Whatever the domain was at the very beginning, even if you've done some algebra, some stuff, whatever, that doesn't change the fact that your domain is still what it was. Yeah. So when I graph this, well, I'm going to essentially graph the line h of t equal to t plus 8. So if I was graphing a line, how do I know it's a line? I mean, I guess I know it's a line because it's linear, because you have a t raised to the first power and no other powers. That's how I know it's a line. And if I'm graphing a line, I usually like to graph the x and the y, or I guess I should say, right, it's not x and y here, but we're still right. I mean, I'm gonna be honest. When I draw a horizontal and vertical axis, even if it's t and h of t or some other letters, I'm still thinking x and y. That's just where my brain goes. So if I was gonna find the y-intercept, I would set t equal to 0. Set t equal to 0. H of 0 is going to be 0 plus 8, which is 8. So my y-intercept is 0, 8. And my x-intercept, if I set h of t equal to 0, that's going to give me 0 equal to t plus 8, or -8 is equal to t. So over here, there's my x-intercept, or my horizontal axis. So when I draw this, it's going to connect the dots. Whoops, try to connect the dots and make a straight line. However, I have to remember, and I've kind of left myself not quite enough room here, but I'm going to make it work. At t equal to 3, I'm not allowed to plug in t equal to 3. So I've got a hole right there where t would have been 3. T can be anything else. T can be 2.9 or 2.999 or whatever. And if you plugged in t equal to 2.9, you would get h of t equal to 10.9. And if you plugged in t equal to 2 point as many 9s as you want, you would get y or h equal to 10 point as many 9s as you want. So you're getting really, really close to 11, but you're not actually getting there. So here the range would look like everything but what? Everything but 11. We don't get 11. That's the only y value we're not getting. We get every other y value. So here the range is -infinity to 11 union 11 to infinity. It's a little tricky, but when you have holes, you essentially exclude those values. No, don't be sorry. So the way I got 11, so here's how you typically find the holes in the graph. If you've done some canceling like we did here, and you're essentially saying, well, okay, if you look at just that function there, h of t equal to t plus 8, it no longer looks like t equal to 3 is a problem, right? If I just said that's your function, and I asked you what the domain was, a normal person would say, well, the domain is everything, right? There aren't any problems, but we have to remember that, oh, 3 wasn't in the domain. But what I'm going to do is I'm just going to plug in 3 anyway. If I plug in 3, 3 plus 8 is 11. So I'm essentially seeing what I would have gotten if that point existed, and then kind of just plucking it out of the graph. To kind of go along with this, just because you have a hole somewhere doesn't necessarily mean you don't still get that value in your range. Let me draw you just kind of a weird picture to illustrate the points. Okay, we got that. So what if my graph looked like, make something up. Sure, so I'm going to have something like this. And let's say that this point here is, I don't know, -5, comma 2. Oh, sorry, you can't. So let's talk about domain and range real quick here. So for domain, what is definitely missing from the domain? What X value is missing? Yeah, there's only one choice, -5, right? We've got every other X value, right? I've got all these X values over here. I've got all these X values over here to the right, but -5 is missing, and I didn't fill it in somewhere else. So our domain is everything from -infinity to -5, union -5 to infinity. Now, here's a good question, I think. Is 2 in the range or not? It's not necessarily an easy question. It looks like it could be missing, but it also looks like maybe we have it. So even though it's missing there, I'm still getting 2 for sure, somewhere there or somewhere there, right? There's another place on this graph where I still get the Y value that's missing. What I should really say is that you can get the same Y value many times on the graph, right? It's okay to get the same Y value all the time because you're not breaking rules, but you can only get each X value once, right? If you had the same X value more than once, you'd be breaking the vertical line test and then you wouldn't be a function. So here, our range is still everything because we definitely have, at least the way I've drawn this, we definitely still have all the Y values even to. Cool, that's kind of not a bad example. Let's see. Oh yeah, let's talk about some piecewise functions for a second. And let's talk about my favorite piecewise function first. Here's my favorite piecewise function. F of x equal to the absolute value of x, which you might not, at least at first, recognize as being a piecewise function. But let's draw it, and then we'll talk about what makes it piecewise. So I think everyone knows how to draw that absolute value of x. It looks like the letter V. I mean, not how I would ever really draw a V, but like it's a really wide V. Here's my absolute value of x graph. Does make a 90-degree angle there at the origin. And here's what I want you to notice. Over here on the right side, where x is greater than or equal to 0, what does that line look like? It's like the favorite line everyone has, right? It's just y equals x. I think, right? Y equals x? Yeah. Y equals x. So over here, when x is positive or non-negative, our function is just x. Okay, but then on the other side, what does that line look like? What's the slope of that line? Negative, right? It's a -1 slope. That's y equal to -x. So over here, when x is less than 0, our function is actually -x. But that is exactly what it means to be a piecewise function. For what's that? For some domain, the function is equal to one thing, and for some other part of the domain, the function is equal to another thing. Oh, I'm trying to remember your name. Tara. Oh, it doesn't matter. You can pick either one. They match up. Right? I could have put the equal to part here instead of here, and it would still give you the same piece. Because basically, whether f of x equals x or f of x equals -x, when you plug in x equal to 0, well, here you get 0, and here you get -0. You have to put it in once, but otherwise, so I will just say, if I wrote my function like this, is f of x equal to x when x is positive, and the line -x when x is negative, I wouldn't have the entire function. I'd be missing the origin. So I need to put it somewhere. But you can literally pick either piece. It doesn't actually matter. So I'm going to put it, I don't care actually. I'll put it here. So graphically, I think this makes sense, right? Like you be like, oh yeah, this is the line, right? Here's y equals negative x, here's y equals x. I just want to say this because it's something that people sometimes get confused about later. And they're like, oh, the absolute value of x is negative x if x, right? But we're trying to make it positive, right? But the thing is, to make a negative number positive, you negate it. You do a double negative to turn it into a positive. So when we write, like the absolute value of 5, well, since 5 is already positive, you just get what you started with. But when you do the absolute value of negative 5, yes, you get 5 at the end, but the way you transform negative 5 into positive 5 is by saying, oh, well, since negative 5 is less than 0, we do the negative of that number, which is 5. That's why the absolute value of x is negative x if x is already negative to turn it into a positive. And it is a piecewise function. Okay. And I guess since we're here, we might as well talk about it. The domain of this function is clearly, well, maybe not clearly. Sometimes I feel like I've used the word clearly. I try not to, but it's a bad habit of math people. It's something that has seemed clear to me for 25 years, might not be clear to everyone else. So I will try not to say it quite so much. But here the domain is definitely everything. We don't have any of the 3 usual problems. And then the range, all right. I feel like when I ask the range question, I imagine people have still heard of the limbo. It's not something anyone should ever do, but the dance where you like dance under the pole like that. I always want to say for the range, how low can you go? How low, right? Like they say, how low can you go? They say that they used that definitely people said I've never limboed. Well, no, maybe. Anyway, how low can you go? 0. So that's the bottom of the range. The less fun question, how high can you go? Right, forever and ever, infinity. As high as you want. Okay, let's look at another piecewise function. A more typical piecewise function. Let's say we have, what do we got here? Sure, we'll do, yeah, we got time. Let's look at f of x equal to piecewise function 5 minus 2x when x is less than or equal to 1, and 5 plus 3x when x is greater than 1. Yeah, that's a horizontal. We'll do one like that next. Yeah. So for something like this, well, first of all, when you have a piecewise function, you can have domain issues if someone left something out. Just as a quick example that we're not going to graph, but for example, if someone said my piecewise function was, and I'm just quick example. If someone said my piecewise function was something like, I don't know, sine of x when x is less than or equal to 0, and cosine of x when x is bigger than pi, we're missing everything between 0 and pi. And if that's the way they decided to define it, great. The domain would be everything from negative infinity up to 0 inclusive, union everything from pi exclusive to infinity. But usually with piecewise functions, we typically use up all of the domain. There's no requirement to, it's just what people usually do. I suppose I should ask it since I'm here. What's the range of this function? Ooh, it's a good question. What does sine look like? What does cosine look like? The same, essentially. Right, and it goes as low as -1 and as high as +1. That's definitely a useful thing to know about sine and cosine, is that unless you have a very limited domain, you're typically going to get the whole range from -1 to +1. So here, yeah, the range would be -1 inclusive to +1 inclusive. But this one is a totally different thing. So domain is everything. I feel like it feels kind of silly to write it, but I'm going to write it. And now we do really need to graph it for the range, or for the range. So I'm going to observe that both of these pieces are lines. So if I was going to graph y equal to 5 minus 2x, and this I will say, I mean, when I'm graphing a piecewise function, I usually kind of graph each piece and then combine them together. So for y equals 5 minus 2x, I'm going to find the intercepts. The y-intercept would be 5. If I set x equal to 0, y equals 5. And the x-intercept, if I set y equal to 0, I'm going to get 5 minus 2x equal to 0. So 5 equals 2x. So 5 over 2 equals x, or 2.5. So my graph, my line looks like that. Now I don't actually want all of that line because I only want y equal to 5 minus 2x when x is less than or equal to 1. So essentially over here at 1, that's where I'm going to stop. And I only want all of this here. And I'm going to plug in 1 to that function to figure out what the y value is. So if I plug in 1, 5 minus 2 times 1 is just 3. At that point, there's the point 1 comma 3. So on my piecewise function, which I've got half of now, this ends at 1 comma 3 and goes to the point 0 comma 5. I kind of think of x equal to 1 as the break point where like we switch from one piece to the other piece. So there's the left half of my piecewise function. And now I want the right half. So I'm going to graph y equal to 5 plus 3x. Same sort of deal. I would still have y equal to 5 as my y-intercept. And then as my x-intercept, I would have, I don't really need the x-intercept. I guess I could find it. X-intercept set y equal to 0. So 5 plus 3x equals 0. So 3x equals negative 5. So x equals negative 5/3. So somewhere over here. So it's kind of like this. But I only want everything from 1 onward to the right. So I plug in 1, 5 plus 3 times 1 is just 8. That's the right point I want. And I actually don't want that point, right? I want this function when x is strictly larger than 1. So I'm actually going to get a hole at the point 1 comma 8. So I need a few more points here. Let's see, 5, 6, 7, 8. So there's my weird looking piecewise function. I should have done, oh well. I should have made that piece lower, so it's a more interesting range question. What's the range? How low can you go? Now you guys need to think about limboing when you do range questions. I don't think we can go as low as we can. So I'll say we can go as far left as negative infinity for the x values, but for the y values, how far down can you go? 3, I think, is the lowest we can go. Yes, for sure. Yeah. So the way I got the 1, 3, and the 1, 8, typically when you have a piecewise function, the breakpoints are points where you need to kind of figure out what the values are. So what I did was I took the left piece here and I just plugged in x equal to 1. When I plugged in 1, 5 minus 2 was 3. And even though this function isn't defined for x equal to 1 on the second piece, I'm still going to plug in 1 there to see where I would be starting. Right, like I call it the break point, or the point where you switch from one piece to the other piece. I'm always going to plug that into to each piece. It's a better word I can't quite think of right now. It's like the transition point. No, that's not right. It's the end point of that interval. I'm always going to plug it into each interval. It's an endpoint for it to kind of see what I'm starting or ending with. So that's how I'm getting the 1 through here. And then yeah, the range here is definitely going to be from 3 inclusive all the way to infinity. And just to point out, if instead this had been slightly different and the function had been 5 minus 2x when x was less than 1, and it had been 5 plus 3x when x was greater than or equal to 1, the only way this function would have changed would have been, this would have been a closed circle now, and that would have been an open circle. And that would have changed my range by them being a parentheses for 3 instead of a bracket. We would have excluded. Cool. Yeah. No, don't. The questions are more than welcome. The way I got 8, so just like, so how did I get 3? I plugged in 1 to the 5 minus 2x. So the way I got 8 was I plugged in 1 to the 5 plus 3x. Now I know, right? It's not exactly kosher. I can't actually plug in 1 there because 5 plus 3x isn't defined when x is equal to 1. What I'm doing is saying, I know that x is closer and closer and closer to 1, like 1.0000. Lots of zeros, 1. If I plug that in, 3 times that is going to be 3 point lots of zeros 3. And if I add up to 5, it's going to be 8 point lots of zeros 3. So I know I'm getting super close. But what I'm really doing is I'm plugging in 1 and saying, yeah, 8's the thing I'm going to start at, but I don't actually start at that whole, not a closed point. Let's look at one more piecewise example, and then we'll talk about even and odd functions for a minute. Let me keep my things in order here. I numbered them this time. It's amazing. I can go back and put them in order later if I have to. Let's see. 7. Let's look at this piecewise function. G of x is equal to the following piecewise function. It is -12 when x is less than -3. It is 4x when the absolute value of x is less than or equal to 3. I don't love this, but we'll talk about it. And it's 9 plus x when x is strictly greater than 3. And so even though I graphed the two things separately last time and then put it together, that's not actually really how I do it. What I really do is I just kind of think about each piece as I go, and I go from left to right. So usually, if these are written typically, they'll be top to bottom, leftmost pieces to rightmost pieces. And they are. Here's the leftmost piece where x is less than -3. Here's the middle piece where x is between -3 and 3. And here's the right piece where x is larger. I will say, absolute value of x less than or equal to 3. That just means that x is between 3 and -3. Right? If x was too negative, its absolute value would be too positive. So we get stuck in the middle there. If I was going to, domain. Are we missing anything from the domain? I don't think so. There's no x values we're missing. I think we got them all. Like Pokemon, caught them all. Okay. So range, on the other hand, let's graph this thing. And I'm going to kind of mark out what I think are important points here. So I know -3 is going to be important. I know +3 is going to be important. Okay. So to the left of -3. So over here. And x is less than -3. My function is -12, meaning it's just a horizontal line with a value of -12. That's kind of low. I'm just going to eyeball it. And it's going to be open at the point -3, -12, because it's when x is less than -3, not less than or equal. So here is my left piece where x is less than -3 and the y value is equal to -12. And then when x is between -3 and 3, my function is equal to 4x. That looks like a straight line that goes to the origin, right? It has a slope of 4. And if I plugged in -3, what's 4 times -3? Oh, so I exactly get to fill in this point that was open. Because for this middle piece, when I plug in x equal to -3, I get y equal to -12. And then similarly, when I plug in x equal to +3, I get y equal to +12. So up over here, at the point 3, 12. -3, -12. And I know that y equal to 4x goes to the origin, just like any line that's a multiple of x does. So it's going to do, I tried to graph it so it's going to actually work. Look at that. Okay, good job. Okay. So here's the portion between -3 and 3, and it's y equals 4x. And then finally, from the right of 3, so here's where x is greater than 3. Well, it's going to be the line y equals 9 plus x, which looks like a straight line, but not quite as steep as 4x. It's going to, and if I plug in 3, oh, what do I get? I get 3 plus 9, which is 12. So someone clearly designed this problem so all the points matched up and you didn't have any discontinuities. I would have had an open circle here, but it already got filled in. And then the slope is a little less steep. So there's our interesting looking function. Okay, time for the limbo question. How low can we go? Right, we can't go any lower than -12. That is definitely the lowest we can go. So the range definitely goes as low as -12. How high? Infinity, right? We keep going up and up and up over here. There's your range. It's not too bad. All right. So, oh, I had one more example. Oh, no, that's a different. So let's talk about even and odd functions, because they definitely are something that show up from time to time. They're kind of neat. They have uses. In fact, especially when we get to 17B, we start doing some integration. We'll be really happy to see some odd functions possibly. So let's talk about what visually makes a function even or odd. So here's what I do. When I think about even functions, so even and odd, I have a few favorite functions, as you do when you become a math teacher. You just have favorites. Like there's some that are better than others. And my probably favorite even function is following: f of x equal to x squared is even. I would go so far even as to say f of x equal to x squared plus or minus any constant is also just as good. And so is something like g of x equal to x squared minus 9, for example. If I shift that down 9, right? Because that's what adding or subtracting does when you add or subtract outside of the function, is it just shifts it up or down. So I'm going to shift this down by 9. And my intercepts are going to be -3 and +3. Because if you set that equal to 0, you get x squared equal to 9, which means x is plus or minus 3. And if you draw it well, there's always a caveat in my class. If drawn well, we can see that it is even. And even functions have symmetry about the y-axis. So even functions graphically have symmetry about or around the y-axis. The way I think about that, it means that you can think of it two different ways. You can think of it as this half over here is looking in the mirror and seeing it self-reflected back over there. Same deal here. The mirror is the y-axis. So this half over here is looking in the mirror and seeing the same half reflected over there. The way I actually kind of think about those really is if you flip this graph over the y-axis, it would still look the same. That's how most people do. We cannot, and here's why. So well, you can talk about a function, or you can talk about a graph having symmetry about the x-axis, but the problem is if your graph has symmetry about the x-axis, it wasn't a function. Well, no, so right, you don't have any functions that are symmetrical about the x-axis, except for one. There's one function and one function only that has symmetry about the x-axis, and it is the function y equals 0. The horizontal line, the x-axis, if you reflect it about the x-axis, it still looks exactly the same. It's the only example of a function that is both even and odd. But yeah, so I would say examples of graphs that are symmetrical about the x-axis, so just kind of throw this in there. So not even or odd, but symmetrical about the about the x-axis. Symmetrical about the x-axis. I can think of two good examples off the top of my head. One is a rightward opening parabola, x equal to y squared. but not a function, right? Fails the vertical line test pretty hard. And the other one is a circle. If you have something like x squared plus y squared equal to 9, that also has symmetry about all the axes actually. But again, not a function. So we wouldn't say that this was even because it doesn't have symmetry about the y-axis. It has to have symmetry about the y-axis. How do you check for that? Well, maybe you can graph it, but not everything is easy to graph. And also graphing things takes a long time. Sometimes you don't have a calculator. Oh, there's something cool I was going to show in distance, I think. So the way you check to see if a function is even, so f of x is even if and only if, I should write the only if and only if f of negative x is equal to f of x. Now you can't just check any old number you want. You can't say, well, f of negative 3 equals f of 3, so it works. Or f of negative 4 equals f of 4, so it works. It has to be true for every x. So let's check that g of x is even. So is g of x equal to x squared minus 9 actually even? Well, I'm always going to start, whether I'm trying to see something's even or odd or neither, I'm going to start with g of negative x. I'm literally just going to substitute in a negative x for every x that there is. When I do that, I'm going to get negative x squared minus 9. And then I'm going to simplify. What's negative x times negative x? Sorry, x, right, x squared. But it definitely is positive, like you implied, right? Because the negative times the negative is positive. Or more generally, you could have said what's negative x quantity squared? It's positive x squared. But I really like to remind myself, oh yeah, when you square something, you're just multiplying it by itself. And the negative times the negative is definitely positive. So this is positive x squared minus 9, but that's exactly the function we started with. So this checks out. G of negative x, or I should say g of x equal to x squared minus 9 is definitely an even function. It has the right symmetry, and more importantly, or as importantly, when you check the actual condition, you get what you need. Okay, let's talk about odd. So odd functions, well, here's my favorite odd function. It's actually, this is not my favorite odd function. So I'm not that good at drawing it, but it's a good example to have. F of x equal to x cubed is odd. And again, I'm not great at drawing it, so I'll do my best here. Looks like this kind of. And I always feel like my graph doesn't really do it justice. So what we like to say about odd functions is odd functions have what we call, there's actually two ways of naming it. You can either say it has have rotational symmetry, or more likely symmetry about the origin. What we mean by this is that if you were to watch it again, there's two ways of saying it. If you think about the rotational way, if you rotated this graph 180 degrees, either clockwise or counterclockwise, about the origin, it would look the same. And it totally would, right? If you took this and, well, in fact, you know what? I actually can. If you rotate this 180 degrees, it looks the same. Or if you were to reflect it in both the x and the y-axis, it would look the same. And it does. A couple other examples of functions I like that are nice, odd functions. An even easier one to draw, although it feels kind of boring, is f of x equal to x. That's also an odd function. It's kind of not very exciting. And then probably my actual favorite one to draw is f of x equal to x cubed minus x. That one just has a little more flavor to it. It's got intercepts at 1, 0, and -1, and it looks kind of like this. And I feel like it just better kind of shows off the oddness. Two other really great functions that are even and odd are cosine and sine. Cosine is definitely an even function. Sine is definitely an odd function. Nice, right? I'm gonna write that down actually. Cosine of x is even. Sine of x is odd. And then the way you would check for oddness is similar to how you would check for evenness, except instead of wanting f of negative x to equal f of x, odd functions, I'm sorry, not quite what I said. What I want to write is f of x is odd if and only if f of negative x is equal to negative f of x. Essentially, what we're saying here is that f of negative x, which is the reflection in the y-axis, is the same as negative of x, which is the reflection in the x-axis. So you put a negative out in front of the function, it reflects it around the x-axis. We put it inside the function y-axis. We can check. Let's actually check this last one here. So we're going to check that f. You're welcome. The f of x equal to x cubed minus x is odd. So I'm always going to start with f. So here's the really good. When I'm usually no one's going to be like check it's odd, check it's even. They'll be like, is this function even or odd or not or none of the above? And so my process usually is to go through first even, then odd, and then if it's neither of those, it's neither. So I'm going to start with f of negative x. And that's going to equal negative x quantity cubed minus negative x. And then I'm going to simplify it before I start asking myself what it is. Negative x times negative x times negative x is negative x cubed. And negative x is positive x. And then I usually like to ask myself, is this even? Did I end up with the same function I started with? Definitely not. Right? I usually write something like, is this equal to f of x? And the answer is no. So it's not even. So then I like to go and say, well, if it's not equal to f of x, I should compare it to negative f of x. So let's go ahead and write what negative f of x is. Negative f of x is negative in front of the whole entire function. So negative x cubed minus x. And then I'm going to distribute the minus sign and get negative x cubed plus x. Oh, are those the same? They sure are. So look. So I see that f of negative x is equal to negative f of x. So we have an odd function. And then if it hadn't been equal, I would say, well, it wasn't even and it wasn't odd, so it's neither. Most functions are neither. It's just that we happen to cherry pick a lot of examples that are like this. Let's look at one. So general statement. When you're dealing with polynomials, like just x to a power plus x to a power plus x to a with coefficients, if all the powers are even, the function's even. If all the powers are odd, your function's odd. And if you have a mix, then it's neither. For example, f of x equal to 2x to the fourth minus 5x cubed. It's definitely going to be neither, but here's how we would show it. So someone could ask you this sort of question on the exam, like determine whether this function is even, odd, or neither. Be sure to show all your work. If you just write neither, it's probably not going to be sufficient. So first I'm going to check for evenness. So f of negative x is equal to 2 times negative x to the fourth minus 5 times negative x to the third. And here's what you hopefully have seen by now. When you have a negative x to an even power, it's going to end up just being positive, or I should say, staying whatever sign it already was. Whereas if you have negative x to an odd power, it's going to end up having a negative and changing signs. So here, I'm going to get just 2 times x to the fourth. And we get a minus 5 times a negative x cubed, which will end up being a positive 5x cubed. Right? The even power thing is staying the same sign. The odd power thing is changing. And is that the same as what we started with? Of course not. This is not equal to f of x. So the answer is no, it's not even. All right, so let's look for oddness. So then I'm going to ask about negative f of x. Negative f of x, I'm just slapping on a negative in front of the whole entire function, and then making sure I distribute it to all the pieces I can. If I distribute this, I get negative 2x to the fourth plus 5x cubed. And then I'm curious, does this equal negative f of x? Oh, sorry, of course it does. That's what it is. Sorry, that's not what I meant to say. Does this equal f of negative x? And the answer is no. F of negative x is right there, and those are definitely not the same. So it's not even, not odd, so it's neither. So f of x equal to 2x to the fourth minus 5x cubed is neither. You can probably just write neither, but you want to be like grammatically correct. So neither odd nor even. I guess I should probably stop since it's 2:58.